Alright, this is going to conclude 1.3, our section on functions. This is day 2. Two things we're going to deal with. First, you can see the definition that's there is piecewise functions. We're just going to evaluate for those. We're not going to graph them yet. And the last thing we're going to talk about is domain of a function. And kind of the common thing is how we will restrict the domains for certain functions here. Okay, you can see your definition, piecewise functions. It's two or more equations over a specified domain. So you'll have a couple equations, but they're going to restrict the values that you can plug in for x. And that's going to be given to you. Now, if you look at the example that you have, here's the example that you have on your handout. We'll say, all right, this is f of x equals, and we're going to have the first equation is x squared plus 1. You know, if you graph that, that would be a parabola. Now, you can plug in any value for x, but they're going to restrict the domain saying you can only plug in values that are less than 0. The second one is x minus 1. You know, that's going to be a line. And then this, you can only plug in values for x that are greater than or equal to 0. Okay, that's the big thing right there. Now, this 0, this is called the boundary point. Whenever you have piecewise functions, this is these right here, this is the specified domain. These are always going to be the same number right here. Now, if you look, the first equation has negative numbers. The second equation, the x minus 1, covers 0 and all the positives. So all in all, when you combine all of them, it combines all the real numbers, all negatives, positives, and zeros, for both equations combined. Alright, now for this, we're going to find the function of 1, function of negative 1, and the function of 0. So as I said before, we're not going to graph these, we're just going to evaluate. Now to do function of 1, all we're doing right here for function of 1 is, where do I plug 1 in? 1 is the x. So when I look at both inequalities for the specified domain, this is where it's going to satisfy. If you plug 1 in here, well, 1's greater than or equal to 0. So that means we're going to use this equation. So I'm just going to plug 1 into that x. So it's just 1 minus 1 equals 0. It's as simple as that. That's your answer, 0. Okay, if we do the next one, function of negative 1. Now, negative 1, the first equation, the x squared plus 1, that's where we're only plugging in values for x that are less than 0. This is it. Right? If you plug negative 1 here, that's a true statement. Negative 1 is less than 0. So I'm just taking this negative 1, I'm going to plug it right into there for that x squared. So when we do that, right, I have parentheses, negative 1, quantity squared, plus 1. Negative 1 squared is 1, and then when you add 1 to it, you get 2. And that's it, that's your answer. Okay, the last one, we have function of 0. This is our boundary point. Now, whenever you have to evaluate for an x value that's your boundary point, basically the equation you're going to use is the one that's underlined, which turns out being the second one. Let's do this one in purple. This is where it's underlined right here. That's where it equals 0. Okay, you might look at the first and say, well, there's the 0, but it's not underlined. So I'm just going to take 0 and plug it into this x. So it's just 0 minus 1, which gives us negative 1, and that's it right there. So there's your only thinking. You're going to have these piecewise functions, which could be two or more equations. They're going to be specified over a domain. When you evaluate this in function notation, your thought process is, all right, where do I plug this in? Do I plug it in the first equation? Do I plug it in the second equation? Or if I even have more than two, do I plug it in the third equation? And then once you do that, you plug it in and you evaluate it. Okay, last thing we're going to talk about is domain of a function. Now, most cases, for most equations and functions, it's all real numbers, the domain, meaning you can plug in anything for x. I'm going to show you two classic examples where there's restrictions. Okay, I'm just going to put example. First classic example is if you have 1 over x. Second classic example where you restrict the domain is if you had square root of x. Okay, if I had 1 over x, think of it, you could plug in any number except for 0. You can't have 1 over 0. So your domain for this is going to be all real numbers. That's our notation for all real numbers, except x cannot equal 0, because that would give you undefined. We see that example a lot, so you can never divide by 0. Okay, the second one, the square root of x, for that example, ask yourself, all right, what values can we not plug in for x? Meaning you would get undefined, or you would get error on your calculator. You can take the square root of any positive number. You can take the square root of 0. Square root of 0 is 0, but you cannot take the square root of negatives. So whenever you have square root, and whatever expression you have inside here, that's got to be greater than or equal to 0. Because I said before, you can take the square root of 0, and you can take the square root of all positive numbers. So this whole expression has got to be greater than or equal to 0. This is your domain. Now the other way of listing this, and I didn't do it for the first example, if you put this in interval notation, I don't think you've seen this before, and I'll explain this more as the year goes on. X is greater than or equal to 0. We could put this in interval notation. I'm going to put brackets. The reason why I put brackets is because this is underlined, meaning that 0 is included. If it wasn't underlined, then I would put parentheses. And if it's greater than or equal to 0, well, there's no end. This goes all the way to infinity. And there's no ending for infinity, so I put parentheses there. So that, and you could use either one. I do not care which one you use. X is greater than or equal to 0, or 0 to infinity for interval notation. Okay, let's look at some examples where we're going to take the domain of them. Okay, so we're going to find the domain. So there's going to be restrictions, and there are going to be these cases where we have a fraction or we have a square root. Okay, we'll keep the next one. Let's keep this simple. We're just going to have g of x equals 1 over x plus 5. So you have a fraction, you can't divide by 0. So x plus 5, when that equals 0, is when x equals negative 5. So our domain right here, it's all real numbers, except x cannot equal negative 5. Okay, let's look at another one. Let's do another one again with fractions since we're on that. Let's go f of x equals 16x over 6x squared plus x minus 2. Now this is going to be easy as number 2. I have to take this entire quantity and I have to set it equal to 0. And I'll even put a line through it. It can't equal 0. Now this, you always want to try to factor it. And I believe this would factor here to 2x minus 1 and 3x plus 2. Now remember, this quantity can't equal 0. Let's say it would give you 6x squared. Your outer terms plus 4x. Your inner terms minus 3x. Good. So that gives you plus x. Negative 1 times 2 gives you that negative 2. Good. So this works. So then this, your answer is your domain. It's all real numbers again, except now there's two values that x cannot equal. For this 2x minus 1, if you set that equal to 0, you would add 1, then divide by 2. So it can't equal 1/2. For this 3x plus 2, you would subtract 2 and then divide by 3. So it would be negative 2/3. Okay, let's look at an example where we have a square root. Okay, last example. Okay, when we have the square root, for this one, we're going to have h of x. This equals the square root of 4 minus x squared. Now I have to take this entire quantity. This entire quantity has to be greater than or equal to 0. So I'm going to put domain. This 4 minus x squared, it's got to be greater than or equal to 0. Well, I could get that x squared by itself. I could add x squared to each side, so I'd have 4 is greater than or equal to x squared. I like having the x squared written first, so it's x squared is less than or equal to 4. Then if I take the square root, right, square root of x squared is x, then I have less than or equal to, and then remember I get plus or minus 2. Now here's the rule to remember. If you have inequalities for the positive, for this positive 2, keep the same inequality. So it's going to be x is less than or equal to 2. Then for the negative, for this negative 2 here, I'm going to change the inequality. I'm going to reverse it. So it's going to be x is greater than or equal to negative 2. So this is going to be our domain right here. And if you actually graph this, I'm going to actually graph this on a real number line. Here's negative 2, this is 0, this is 2. If you had x is less than or equal to 2, it would go this way. If you had x is greater than or equal to negative 2, they would both meet. These are the only numbers you can plug into this this equation, and it makes sense. Look, if you have 3, you can't plug 3 in. If you plugged in 3, you would get the square root of 4 minus 3 squared, which is 9. And 4 minus 9 would give you the square root of negative 5. You can't do that. You can't take the square root of a negative. So this, you could list this. We could put an end in here. This is your domain. Or if I put this in interval notation, it's just negative 2 to positive 2. That's it. Those are the only values that you can plug in for x, so that you're taking the square root of positive numbers. So classic examples right there. You know, if you take the square root, it's got to be greater than or equal to 0. You know what? Let's just do one more example. That's very similar to this. And it's a square root. Okay, we're going to find the domain, and we're going to go f of x equals the square root of x squared minus 9. Okay, when we do this one right here, again, that whole quantity, x squared minus 9, it's got to be greater than or equal to 0. So I have x squared minus 9. That has to be greater than or equal to 0. Can't take the square root of negative numbers. I add 9 to each side. I have x squared greater than or equal to 9. I take the square root of each side. I'm going to get x squared greater than or equal to, let's put here plus or minus 3. Now again, for the plus 3, I'm going to keep the same inequality symbol, so it's x squared is greater than or equal to 3. And then for the negative 3, we change the inequality symbol to x. Whoops, I'm sorry, this should be, we should be getting rid of this x squared, it's just x. And then for the last one, it's x is less than or equal to negative 3. And if you really want to make sense of it, again, you can draw that real number line. It's going to be very, very similar to the last one. We have negative 3, 0, we have 3. Okay, x is less than or equal to negative 3. Actually, it's going to be a little bit different. X is less than or equal to negative 3. And we're going to have, which goes to the left, and we have x is greater than or equal to 3. So this is actually going to be the opposite. So I'm going to erase this. Instead of using and, this is our disjunction. This is where we use the word or, because it goes different ways. So it's good. We took an example of each where it's or, where they go different ways, or it's where they converge, like it did for number 4. So that's an and. So you can list this. This is your domain right here. If you put this in interval notation, okay, the negative 3 goes to negative infinity, and then it goes to negative 3. That negative 3 is included. I put U for union, and then it starts back up at 3. 3 is included, so that's why I have brackets, and that goes all the way to positive infinity. Alright, so there it is. You know, we took a look at 2 examples then for when you had a domain that was restricted. The 2 classic examples, you can never divide by 0. And the last couple examples we looked at, you could only take the square root of positive numbers.